All right, so the next setup was to calculate the pH at the equivalence point. So I want you to think about this one for a little bit. We started off with 0.05 moles of the acetic acid. Now at that point, at the equivalence point, by definition, we will have added 0.05 moles of the hydroxide. To be clear, I know because there's two bases floating around here. So in this case, we're talking about the strong base, the titrant hydroxide. So we can do a couple quick calculations here. So the volume of the base added at this point, we previously determined, is going to be 250 milliliters, which means our total solution volume is now going to be 350 milliliters or 0.35 liters. And at this point, now if we were to determine the concentration of these species before the hypothetical, before the reaction idea, we would have 0.143 molar acetic acid and 0.143 molar acid hydroxide. If you're wondering why I'm calculating these hypothetical concentrations, it's to actually get the concentration so that you can work it into the reaction table, which is most conveniently done in concentrations and not amounts at this point. But so now you've got these hypothetical concentrations, the hypothetical pre-reaction concentrations, and now we'll see what we can do with those. All right, so what exactly are we looking at here in our flask of, in our titration flask? Well, we've got acetic acid and acetate and hydroxide, possibly. So these are the concentrations that we calculated from the previous slide. So after you've added everything, but before any reaction or hypothetical starting point here, we have a 0.143 molar concentration of acetic acid, no acetate, and a 0.143 molar concentration of hydroxide. So what happens if the reaction is complete, and what do we end up with? Is that we are going to lose 0.143 molars. The concentration of the hydroxide is going to go down by 0.143 molar to 0. And the acetic acid will undergo a similar change because, well, that's what happens when you titrate and you stop at the proper point, which will leave us with a gain in acetate concentration of 0.143 molar, giving us a 0.143 molar concentration once we stop. So can we just go ahead and calculate the pH with the Henderson-Hasselbalch equation like we did before? And the answer here is a resounding no, because we do not have a buffer anymore. We don't have any more acetic acid. So we cannot use the nice handy-dandy Henderson-Hasselbalch equation. So how do we figure out the pH? Well, it now becomes a weak base equilibrium, that we basically have a 0.143 molar solution of sodium acetate, and acetate, by virtue of being the conjugate base of acetic acid, is itself a weak base. So the equilibrium that we need to look at in this case now is this one right here, which is the reaction of the acetate that we have created by virtue of this titration with water to form acetic acid, back again, a little bit of it, and hydroxide. So this is the regular weak base equilibrium, and this is the reaction that corresponds to the Kb of a weak base. And if we know that the Ka of acetic acid was about 1.8 times 10 to the negative fifth, we can use the relationship that we developed before, namely that the product of Ka and Kb is equal to Kw, to figure out the Kb for acetate, which will give you a 5.6 times 10 to the negative 10th. And let's just take it from here. So we want to use the endpoint of the titration as the starting concentrations for this ice table. So we had 0.143 molar acetate, no acetic acid, no hydroxide. Because we are completely devoid of those species, we can assume some of it has been produced. So we're going to lose some acetate. We're going to end up with 0.143 minus X molar acetate. And we will also end up with X molar acetic acid and X molar hydroxide. And so we know what Kb is, and it's equal to so here we've got it's equal to X squared, and we can say this is a very small number, so we can approximate that. And that's going to give us X squared is equal to 8 times 10 to the negative 11, which gives us an X of 9 times 10 to the negative 6, which is equal to the hydroxide concentration. And just so you know, remember that this is going to be equal to the acetic acid concentration, hydroxide concentration, divided by the acetate concentration. And now one very important thing to remember is that this is the hydroxide concentration. And this is kind of a common goof that I see, because you're typically thinking about the acid equilibrium a lot of times, and you forget that in this case X is equal to the hydroxide concentration, but fret not. That you can get to the hydronium calculation for any aqueous solution by virtue of the Kw expression right here, and that gives us 1.1 times 10 to the negative 9 molar. Giving us a pH of about 8.95. Right. And so this is the calculation for the pH at the endpoint of a weak acid-base titration. All right, so that was a lot to take in. So what are the main points here? So typically, what we're going to ask for here is the pH at a certain point in the titration. And basically there are there's 4 midpoints. Number 1, initial. So this is before you actually add any of the titrant. And in this case, now first of all, this applies for a weak acid titrated with a strong base. So initial, before the titration. It's basically a weak acid pH problem. Intermediate, so this is after starting. But before the endpoint. And in that case, you treat it like a buffer problem. At the endpoint, it's a weak base problem, or you can treat it as such. And finally, if for some reason we're asking about something beyond the endpoint, In that case, the pH is dominated by the excess hydroxide. And that's how you figure that out. So that's the basic wrap up. Everything is sort of reversed for the titration of a weak base with a strong acid, and I've got a YouTube example for that as well, so make sure you check that one out.